I know there's a formula for the area of this sector. The question is, how do I find it? And there are a couple of different ways to do this. You could have already seen this formula in your pre-calc class, back in trig. But I'm going to assume that you don't remember it from there. So, if I know the radius of the circle, and I know the angular width of the wedge of my sector, how much of the area of the circle is it? It's clearly a fraction of the whole circle, right? So the real question is, what fraction of the whole circle? Formula for the area of a circle? Great. So my question is, what fraction of the circle is taken up by this wedge? Only if I know that that angle is exactly 60 degrees, right? But I don't know what that angle is. That angle could be 37.23. It could be pi over 7 radians. It is a crap. But I just compared the size of the angle. When you said 1/6, I went, well, that would be a fraction of 360 degrees, wouldn't it? Let me think in radians, because I'm a geek and I like that. The whole circle has an angular width of 2 pi radians. This piece only has an angular width of theta radians. So if I were to take theta over 2 pi, that would tell me the fraction of the whole circle eaten up by my wedge. Oh, so that's the proportion between this angle and all the way around. Well, that's going to be the proportion of the area. So the area of my sector is this much of the area of the whole circle. Well, look at what happens. Pi's cancel, and I get the area of my sector is 1/2 r squared and theta. Multiply together. Okay. So effing what? A polar curve is described as some function of theta. I don't know what the curve is. I've just made up some picture at the moment. But let's suppose that I said, I want you to find the integral. Wait a minute. Normally we think of integrals in terms of x and y, but now I'm thinking of this as a function of theta. That means I'm integrating in terms of theta, which means instead of starting at some x on the left and going to some x on the right, I'm going to start at some angle and go to some other angle. So I can think of this area here as the area under, well, it's probably a bad word. I should use inside. The area inside the curve. And that's bounded by two values of theta. We can actually picture this like a fan unfolded, right? We start with it closed over at theta 1, and we spread it open until we get to theta 2. We get a bunch of little wedges, don't we? If I picture that fan opening, there are ribs in a fan, right? Hi, I'm from the South, y'all. That sort of fan. Well, then I get these little ribs that are lines like that. I can approximate each wedge like it was a wedge here in a sector. But each wedge then looks like this. But instead of r, I'll use my equation. And I don't know what the change in the theta is. That'll be d theta. Oh, let the width of each one go to 0. Let the number of them get bigger and bigger. This becomes an integral. Ta-da! I have a way of doing integrals in polar coordinates. But instead of thinking of area under, I think of area inside. Inside what? Well, let's take a curve we've already dealt with. What's that picture look like? You have a graphing device. You do not have to have this crap memorized. It could in height, but you don't have to. Aha, it's across the y-axis because that's a sine. If it was a cosine, it would be across the x-axis. I'm good with that. I'm very happy about that. So, I would like to know how much area is inside this. This is symmetric. So if I can figure out the area in that first petal, the one that's in the first quadrant, then I'm good, right? I'll just multiply by 3. All I really need to figure out is the area of this one piece. Yes, Leo. Hold that thought. I don't know that yet. Let's figure that out. How do I get there from here? Because that's what I need to figure out to be able to use this. I need to know what are the bounds in theta. Now, Leo, you said 0 and pi over 3, but how do we know that? Absolutely. I can use the trace, and then I hopefully recognize the decimal that is pi over 3. Because remember, when I use the trace button, it gives me really ugly-ass decimals. I don't think I'm going to recognize the decimal for pi over 3, so I would like to find another way to find that out. Again, but I don't know if that decimal off the top of my head. So I'm going to find an analytic way. But if that's the case, then it should go to 2 pi over 3, shouldn't it? Remember when we did this, we went over the pedals twice. I think that's part of my problem. So I really think I should need an analytic method for getting it. But let me think about that. I know that right here, what's the radius at that spot? How far away from the origin am I? 0, I'm on the origin. So if I think of where is r equal to 0, well, that's when sine of 3 theta is equal to 0. When is sine equal to 0? It does it a lot, doesn't it? Aha! That means that 3 theta is equal to 0 or pi. There we go. Divide by 3, and I get my bounds. To be exactly as you said, Leo, 0 and pi over 3, but I'm not convinced that I will know the decimal all the time, so I'll do this sort of a method instead. And now I can set up the integral to find the area inside that loop. By doing the integral from 0 to pi over 3. Now, the 1/2 in that integral could be pulled out front. It's a constant. I'm perfectly fine putting it out front or leaving it inside, depending on whether or not it helps me inside versus outside. And then I need f of theta, that's our r, squared. D theta. Oh, look! Chapter 7, Section 2, trigonometric integrals. It's a good thing to remember how to do these, right? This square. I need one of those trig formulas. Leo? I need that half angle formula. I can never remember whether it's plus or minus. I have to go through and derive it every time because I'm silly like that. If you remember, that's fine. So to get rid of a sine squared, I replace it with 1 minus cosine of twice that thing over 2, which means this becomes one minus cosine 6 theta over 2 d theta. And again, I can pull the over 2 out in front. What's my antiderivative? Leo? There's a u substitution there. U equals 6 theta. There's no 6 out in front, so I get a 1/6 instead. Oh, don't forget there's still that 1/4 out in front. And then this whole thing gets a 0 and a pi over 3. Plug it in and tell me what you get. when I put pi over 3 in, 6 times pi over 3 is 2 pi. When I put 0 in, 6 times 0 is 0. What's sine of 2 pi? Same thing for sine of 0, which means the only thing that survives is that pi over 3. But that's for one pedal. So for the whole thing, I would need to multiply by 3. Questions? Some of you are staring at this board like it's offended you mortally. So tell me what's going on. So as long as I have an area that is well defined inside a curve to the origin, this is exactly the piece I want to do. But I need a picture. I know I said it back in Calc 1 when we were doing the areas in between curves and the areas for definite integrals. And I said it back when we were looking at graphs that went sideways versus going up and down as opposed to going left to right. A picture helps. What's the picture look like here? Now, if you remember the shapes we did yesterday, you can tell me what both of those shapes are before we actually draw the picture. But that's only if you remember all the shapes we did yesterday. We did 2 sine theta, 2 cosine theta, and those gave us circles. So I'm pretty sure that this top one is a circle. Should be a circle, radius 3. Since it's a minus sign, it should be on the left rather than on the right. What about the 1 minus cosine theta? I think we did 1 minus sine theta in class. What did that look like? That's our heart shape. So I think I'm going to get a cardioid, but instead sine would have made it go up and down. Cosine is going to make it go left to right. So I get a circle and I get a cardioid. And we said that the circle was which equation? The negative 3 cosine theta. So I'm going to write that down. Circle, cardioid. All right. If this is what I'm after, then I want the area inside the circle, outside the cardioid. That's this crescent moon shape here. I'm going to make a copy of this as a crappy picture so that I can refer to it later. Cardioid, circle. I'm looking for this area. Inside the circle, outside the cardioid. I did say it was a crappy picture, and boy, does that one suck. But it gets the idea across, which is really what I need. Now, my first reaction is to ask the same question I asked last time. If I want to do an integral in polar coordinates, I need polar limits. There's some angle where these cross, both at the top and at the bottom. How do I find those numbers? Magic. No. Well, that's where the curves cross. That's where the radii are the same. All right, so I move this over here. I get -2 cosine theta equals 1, or cosine theta is -1/2. Ladies and gentlemen, I'm back to my unit circle. Where is the cosine of theta equal to -1/2? That'll give me this one, because 2 pi over 3 is in the upper quadrant. Second quadrant, absolutely. What about this one? Aha. By symmetry, it's the same angle, so it's the same reference angle. It's just down a quadrant. Perfect. Okay. I want the area inside the circle from here to here. And then I want the area in the cardioid. And I subtract. Outside curve minus inside curve. Hey, wait a minute. Chapter 6, section 1, last semester, the area between two curves, we took the top curve minus the bottom curve, right? Because we were thinking of strips that went vertically. Now I'm thinking of lines for a fan that go out. So I think of the outside versus the inside. The little piece of fabric that is the fan itself would be here. So outside equation, that's our circle. Inside equation, that's our cardioid. All right, I can tell you right now I'm going to end up with a cosine squared in here, which means I'm going to need the other version of that square reducing half angle formula. to do later, but I'm also going to have to multiply these out in order to do the integral, because there's no u substitution floating around here at all. 1/2 9 cosine squared theta d theta, then another 1/2. Now this is all a binomial, so it's first thing squared minus 2 times the first thing times the second thing plus the second thing squared. Notice there's a 1/2 in front of both pieces. The bounds are the same, which means instead of doing two separate integrals, I can combine these into one integral. I have 8 cosine squared minus a minus becomes plus 2 cosine theta minus 1. Since I took the 1/2 out front, if you would like to put the 1/2 in, that's fine. I'm not going to care. Problem I have is right here. What happens there? It isn't Final Jeopardy, people. Come on. What do I do? The other one of these, right? Instead of the 1 minus, because that was for sine, it's going to be the 1 plus. And again, I'll be able to do more simplifying algebraically because of what I've got here. I'm going to get a 4 and 4 cosine 2 theta here. So I can combine the 4 and the 1 at the end to give me a 3. And again, because that's cosine of 2 theta, there's a u substitution required to do that integral. The rest of those integrals are easy because the rest of them are simple antiderivatives. I get 3 theta. Here, what's the antiderivative of cosine of theta? But here, it's cosine of 2 theta. I need a 2 out front. I have a 4 out front, so I'll just take one of the 2's, and that becomes 2 sine 2 theta. U equals 2 theta, du is 2 d theta, so I get a 1/2, and that with the 4. And then remember, that's still that 1/2 out there, and now I have 4 pi over 3 on the top and 2 pi over 3 on the bottom, and I need to plug and chug and now get a number. Fortunately for me, a lot of these numbers end up canceling out. 3 times 4 pi over 3 is 4 pi. 2 sine of 8 pi over 3. What's the sine of 8 pi over 3? Oh, wait a minute. 8 pi over 3 is a whole circle and 2 pi over 3. So the sine of 8 pi over 3 is the same as the sine of 2 pi over 3. That's in the second quadrant. So its sine is root 3 over 2. Plus 2 sine of 4 pi over 3. Where's 4 pi over 3? Say again? Third quadrant, which means its sign is negative. Hey, wait a minute, what's going to happen right there? Those two cancel each other out perfectly. Now I put in the 2 pi over 3. 2 pi over 3 times 3 is 2 pi. 2 sine of 4 pi over 3, we just did that. And then 2 sine of 2 pi over 3. Wait a minute, that's negative, that's positive. Those cancel, those cancel. What's left inside? 2 pi. The area in that crescent shape is exactly pi. Please note, in the picture that goes with this graph, how many times do those curves cross? They both go through the origin, don't they? Matter of fact, if I zoom in, there's the circle, and there's the cardioid, and they both touch 0, 0. But if I hit trace, when am I at the origin? I'm on the circle right now, yes? Notice that for me to get to the origin, my theta value is pi over 2. Switch to the cardioid. For me to get to the origin, my theta value is 0. So technically, while both of those points touch the origin, they don't do it at the same time. Whereas out there at 2 pi over 3, those are actually at the same point when the angle is the same. Same thing down at 4 pi over 3. They're at the same point when the angle is the same. They both go through this point, but they don't do it at the same time. Same theta value, which is why that point is technically not an intersection. It's an overlap. Imagine, if you will, that our little crawler here is a car on a road. At 2 pi over 3, There's a car on the circle, there's a car on the cardioid, there's a car accident. At the time, 2 pi over 3, both cars are in the same spot. At the time, 4 pi over 3, both cars are in the same spot. But both cars are never here at the same time. Technically, the curves overlap, but they don't intersect. The very different thing about the way you think of parametric and polar equations to think of them as actual motion. I think that's helpful when looking at limits, bounds. As a matter of fact, in the textbook, here's a circle crossing a 4-leaved rose. If I just solved it the way we normally do, I would only get 2 solutions. I'd get positive pi over 6, negative pi over 6. So I'm solving cosine equals a number. But I have to add all the multiples of 2 pi to find all the other possible intersections that I wouldn't have known existed if I hadn't seen what the picture looked like. So I think it's always important to draw the picture, look for the intersections, and then find out mathematically, are they intersections? Questions? I can do area, I can do length. Length, that's my arc length piece. All right, wait a minute. How the hell am I supposed to get arc length out of r and theta? If I remember correctly, we had the square root of 1 plus f prime of x squared dx, or we had 1 plus g prime of y squared dy, or we had dx dt squared dy dt squared dt. I'm running out of breath just from listing the options. Wait a minute. That last version thinks of polar as parametric. Remember, we have x equals r cosine theta and y equals r sine theta. So what I could do is I could say x is f of theta cosine of theta, and y is f of theta sine theta. And then I could do this in terms of theta. Oh, this is going to absolutely suck, isn't it? Well, no, it's just going to be not short. But with a little bit of algebra and a couple trig identities, I can actually make this work. What I will tell you is that after all that algebra, this turns out to actually be pretty nice. For your next exam, all 4 versions of DS. will appear on the provided formula sheet. But that means if I want the arc length, I do exactly the same thing. I just bound it in theta. What was the equation we were doing earlier, the three-leaved rows? Sine of 3 theta, right? R equals sine 3 theta was the first problem we did. Well, I could ask the question, instead of how much area is in it, how long is the loop? But we already know what the theta bounds are for one loop. For one loop, that's the same as what we did for our area. We're going from 0 to pi over 3. Here's the problem part. R squared plus dr d theta squared. R squared is sine squared 3 theta. What's dr d theta? R? Aha! Chain rule. And then when I square that, I'm going to get 9 cosine squared 3 theta. Right? If it was cosine squared and sine squared, I'd just get a number. I'd get 1. But there's a 1 in front of the sine. There's a 9 in front of the cosine. So if I peel off one of those cosines, I'd get 8 left. I'm going to tell you right now, that integral makes me want to cry. I don't know how to do it. My first thought was, hey, square root of 1 plus something squared, right? That would be a trig substitution, but then I would have u equals square root of 8 cosine 3 theta. And I definitely don't have a du to go with that. Oh. Literally, I don't know how to do that integral. I don't know what the answer is, which means I really only have 2 choices at this point. I get a Wolfram alpha, or I do that on my calculator. Because we can do a definite integral on here. Math button. I'll hit the right button. Option number 9 is a definite integral. Now I can put in exactly what this thing says. 0 for a lower limit, pi over 3 for an upper limit, square root, not squared, square root 1 plus 8. I need to square the cosine, so I need to put it in parentheses. Cosine 3 theta, close the 3 theta, close that, squared d theta. And because I was in polar mode, it knows that when I hit the variable button to give me a theta. Takes a little while, but it gives me an answer. Talk to me, Maddie. It is quite possible that you will get slightly different decimals out here based on the precision level you've set for your calculator, if you've changed that default at all. So if you go into mode, way down here, no, where is that? Format, no, table. Table set, nope. I've forgotten where that setting is, but there is a way to set the precision level. Are you getting roughly this answer, or are you getting something wildly different? Check your calculator. Are you in degrees? Is your square on the outside? But is your square on the outside in the right place here? Because I saw one person who wrote cosine 3 theta squared there and not there. So it depends on where your parentheses are. Go back and look carefully. This is not an easy thing to type in. Double check it in Wolfram Alpha. Maybe I did it wrong. I'm not 100% sure. I can even type in this version if you'd rather. But because I'm at the point where I don't know necessarily how to do the actual antiderivative in question, I'm going to run into that problem whenever I see an arc length integral, especially in polar. Because in polar, those integrals suck. Which means I'm going to rig stuff for you, or I'm going to tell you to use your calculator. Better? All right. Tomorrow is question and answer day. Sections 10.2, 3, and 4, and your homework is due Monday. I will see you all tomorrow. Bring me your questions. I'm going over to the Enrichment Center, so if you have more questions and have the time,